Hi, welcome. Today we're going to talk about acid and bases, the HAl material for IB chemistry. Now, as you may recall in class, we talked a little bit about some of the HAl material earlier when we talked about the autoionization of water. As you can see from the equation that I have here, water is able to autoionize, to basically break the covalent bond in a heterolytic form to form the H plus ion and the OH ions. And we know that because it's a bond breaking reaction, this is going to be an endothermic reaction. If we write the equilibrium for this, because water is a pure liquid, it does not go into the equilibrium constant, and so the equilibrium constant, which we're going to call for the autoionization of water, Kw, takes the form of the concentration of the H plus ion times the concentration of the hydroxide ion. All right, and at 25 degrees Celsius, this is 1.0 times 10 to the negative 14th. Now, because it's pure water, the concentration of the H plus equals the concentration of the OH minus, because for every water that you break up, you make one H plus and one OH minus. And therefore, the concentration of H plus or OH minus, or hydroxide ion, will be the square root of Kw, in this case 1 times 10 to the negative 14th. All right, and that is going to be true for any pure water. So the idea of neutral water is going to be not so much when you have a pH of 7, but when you have equal quantities of H plus and OH minus. That is the real concept of neutrality. Now, you may also recall that in order to calculate equilibrium, in order to calculate pH, P stands for negative logarithm base 10 of something. So pH is the negative logarithm of the concentration of the the hydrogen ion, the H plus ion, and POH would be the negative logarithm of the hydroxide concentration. We also demonstrated earlier that pH plus POH equals 14 when you measure this at 25 degrees Celsius. All right. Now, since the autoionization of water is an endothermic process, as we increase the temperature, we are going to increase the production or the yield of products, and we're going to make the value of Kw, because the amount of products H plus and OH minus increases, we're going to make Kw a larger number. All right. So the higher the temperature is, the lower the pH is going to be, because the higher that H plus is, because it's negative logarithm of the concentration of the H plus, the pH will become a smaller number. In theory, water becomes more acidic as you make it, as you heat it up. But that is only if we were thinking about pH being a standard that works for any temperature. Neutral, pH is neutral at 7, only at 25 degrees Celsius. If it's hotter, it's going to be greater than 7. All right. So here's a little example of a problem that we could try out, and I'm going to try to work that one out very quickly here for you on the board. Now, as you can see, the equation that we use is the same one, all right? And we have to be aware of what actually happens. Kw is equal to the concentration of H plus times the concentration of OH minus. But because we have pure water, concentration of H plus equals concentration of OH minus. That value is 2.35 times 10 to the negative 7th, and pH is equal to negative logarithm of the concentration of the H plus ion, and when I enter that, it's 6.6 0.28, and that would be my answer. That would be the pH of pure water at 50 degrees Celsius. All right? Now, we also talked about the fact that if we have a strong acid, all right, if we have a strong acid, the concentration of the H plus, because a strong acid completely ionizes in water, the concentration of the H plus is going to be equal to the initial concentration of the acid. And for a strong base, the concentration of the hydroxide ion will be equal to the concentration of the base, as long as the base only is releasing one OH. If the base releases more than one OH, then you have to multiply the concentration by the number of OHs of hydroxide ions that the base is releasing into the solution. So very quickly again, we can see for these two monoprotic acids how we would do this for a monoprotic acid and for a base, a strong acid and a strong base, what we can do. All right. So in the case of this equation, I'm even going to write the equation for you just so you can see what's going on very quickly. So in the first case, we see that the concentration is 0.35 moles per decimeter cubed. The pH for this strong acid is going to be approximately 0.445. All right, pH again has no units, remember that. So it's a very low pH. We have a very acidic solution, and this is because, of course, we have a solution that is for a strong acid. In the case of the base, as we have here, we're going to have twice the number of hydroxide ions as we have amount of barium hydroxide. Therefore, the concentration of the hydroxide ion is going to be 2 times that of the concentration of the barium hydroxide. Notice that for a base, if we have hydroxide, we cannot directly calculate pH. We need to first calculate pOH and then take that in order to calculate the pH. 14 minus pOH equals to the pH. All right? Hopefully that was pretty straightforward. Now let's go ahead and move on to a little bit more complicated ideas. If we actually have weak acids and weak bases, we have to establish an equilibrium because it is only a partial ionization that is taking place. All right. Now, if we have a weak acid, that ionization equation is going to take the form of acid. The unionized acid will ionize into H plus, and the conjugate base of the weak acid. We're going to call the equilibrium constant for this equation. It's just the same thing as a normal KEQ or a KC, but in this particular case, because it's for an acid, we're going to call it K sub A. It's the acid dissociation constant. And it takes the form of the concentration of the hydrogen ion times the concentration of the conjugate base divided by the concentration of the acid. And all of these concentrations, of course, are the equilibrium concentrations. These are the concentrations not when you started the process, but actually once the reaction has reached equilibrium. All right. Now, if we, like normally, do an equilibrium analysis using the equation, initial, change, and then equilibrium concentrations, we should be able to calculate the concentration of the H plus, the hydrogen ion, at equilibrium, and therefore the pH of a solution. So, for example, if we were starting with a solution that had an initial concentration of 1 molar, all right, well, we would put our 1 molar initially where we have it at under initial, and 0 concentration of H plus or H minus. Change is how much, we're going to call it X, we're just going to use the stoichiometry, it's how much of the acid is becoming ionized, and it's going to produce an equal amount of H plus and an equal amount of the conjugate base. And we set up the equation as we have it here, all right? Now, this is useful, and if we work with this, we're going to end up with a quadratic equation. Now, if the value of Ka is given to us, and it's larger than 10 to the negative 5, or even sometimes 10 to the negative third, all right, we have to solve the quadratic equation, or maybe if we're lucky, we can do some square rooting, and we can solve the entire problem. But if this is not the case, all right, we have to solve the quadratic equation if the value of Ka is larger than about 10 to the negative fourth, 10 to the negative third, all right. But if it's smaller, we can do the method of the approximation, all right. And so basically, what we can approximate is a value 1 minus x is approximately 1, because x is so small that the value of x gets lost when you're subtracting it or adding it to an actual concentration, all right, to a much larger concentration. So it would be lost in the decimal places. The significant figures would not register it, all right. So instead of doing the quadratic equation, we can save ourselves a lot of time by doing this. So let's try that for a problem. If we have, for example, a solution that is a 3.50 times 10 to the negative 1 molar of ethanoic acid, all right, and we see that the Ka value of ethanoic acid is 1.7 times 10 to the negative fifth. If you do not know what the value of an acid is, you can check in table 15 the values of the pKa's are given to you, all right? And the value for the pKa for ethanoic acid was given as this. Well, Ka is just the value of the pKa, 10 to the negative value of the pKa, all right? And so you can actually solve that using the values that are given to you on table 15 in the IB data booklet. All right. So let's set up this as an equilibrium problem. The first thing that we're going to do, again, is we're going to write our equation. We're going to put our initial, change, and equilibrium. Now, we really want to analyze the values of initial change and equilibrium, so I'm going to move that equation for Ka a little bit lower just so we have some space. since the value of Ka is so small, I'm going to approximate 3.5 times 10 to the negative 1 minus x to 3.5 times 10 to the negative 1. And I can enter now my values into the equation. When I solve this for x, I can see that x is just the same thing. X times x is x squared. So I can actually write this in this format. And when I take that value and I square root it, I can actually get this number. So I'm just going to go directly to the number that I have there. All right, and we can see that the pH is relatively low, but when we compare it, all right, and I think it's important, when we compare it to the pH of the strong acid we had just calculated, all right, and you look at those two numbers, you can see how much weaker, how less acidic as ethanoic acid is of the same concentration than nitric acid. And so that's one of the things that I really want you to be able to see. Okay? Now, if we are talking about weak bases, we're going to establish a different equilibrium. The equilibrium is we're going to have the base and it's going to react with water and it's going to cause the hydrolysis of water, releasing the conjugate acid BH plus hydroxide ion. All right? Now, the water is a pure liquid, so we're going to leave it out of the equation, and we're just going to take the ions and the initial base. All right? And the initial base could have been charged or not, so just be aware that the signs of the BH plus and the B, depending on whether you start with a conjugate base or not, may actually change. But the structure remains the same. It is the concentration of the products over the concentration of the reactants, and we're going to eliminate the water because it is a pure liquid. All right, so just like before, we want to be able to find the pH of the solution of a weak acid. All right, now how would we do this in this particular case? In this particular case, I have not given you the value of the Kb. And so what are we going to do? We're going to go again back to our tables. And if we look at the backside of table 15, we can find methylamine, which is what we have in this particular case. And it has a value of pKb. And the value of pKb is 3.34. And so when we enter that into our calculator, we find that the value of 3 is going to be 4.57 times 10 to the negative 4th. All right? And we're going to write the equation and again do the entire equilibrium analysis. And again, in this particular case, because the value of Kb is relatively small, even though it's not quite 10 to the negative fifth, we're still going to go ahead and use the assumption. So we can enter the values into the equation. And when we do that, we get that this is equal to the concentration of the hydroxide ion. And again, we obtain the value of pH by first calculating pOH and then subtracting 14 minus pOH. All right? So that is how we would tackle this type of problems with weak acids and weak bases. You also may recall that when we were talking about the Bronsted-Lowry definition, we were talking about the fact that acids and bases can make conjugate pairs. Conjugate pairs are species that differ by an H+. All right? So, if, for example, we were given a reaction in which we want to see how they act, all right? What is the basic power of the conjugate base of a weak acid, or what is the acidic power of the conjugate acid of a weak base, we need to look and do a little bit of analysis. All right. So as you see from the equation that I have here in front, we can see that the acid plus water will give us a hydronium ion. I put the water in this case. We could have left it out. It could just be acid gives us H plus A minus. I just put it there for so you can actually visualize it a little bit better. But if we remove it, this would just be H plus. All right. If we don't put the water in there, it's basically the same. But as the acid ionizes, it creates H plus and the conjugate base. Now, that conjugate base establishes it because it's strong enough, because it's the conjugate base of a weak acid. It's strong enough to interact and act with water. All right, and so it's going to be a base that can actually cause the hydrolysis of water and have its own equilibrium in which the base actually reverts and creates some hydroxide and creates some of the original acid. All right, and so A negative can react with water to produce HA and a small amount of hydroxide ion, and it establishes a value of Kb. Kb in this case is HA times the concentration of OH over the concentration, the original concentration of the H plus, the H minus, the A minus ion. Okay? So why in the world would we ever want to do this? Well, many times we're given salts that have the conjugate base of a weak acid. When you dissolve those into water, they can cause the hydrolysis of water and change the pH. So those are bases that are capable of changing the concentration of water from neutral to, in this particular case, basic. All right, the conjugate base of a weak acid will make the solution basic. It's a conjugate base after all. All right, and so if you dissolve a salt of this type it will have an effect, and you should be able to calculate what the pH is. Now, if you look in your table 15, you will find that the KBs do not include the KBs for conjugate bases. So how can you find this out? How is it possible that we can do this? You may recall that if we multiply one equation times the other, when we add two equations together, the equilibrium constants multiply as the product. All right. Well, what happens if I add the equation for the acid and the equation for the base? If you can visualize that with me, I'm going to do it on the top. All right. And the resultant equation that you get for this, all right, or if we had left one of the waters out, which of course we know is the autoionization of water. So the product of Ka and Kb for a conjugate pair, an acid and its conjugate base, is going to be equal to Kw. And that we can see over here. Again, we can see how those values cancel. So if we do the P for each one of them, all right, the negative logarithm, pKa plus pKb, which would also be equal to pH plus pOH, equals to pKw, and pKw is 14. So this is another way of looking at all of this. So be mightily careful that pH and pKa are not the same thing, and pOH and pKb are not the same thing, but when added together they do end up resulting in the same numbers. So these are the equations that I really want. This is the equation that I really want you to take home. All right. So having pKa and pKb for a conjugate pair allows us then, will be helpful to calculate salt hydrolysis and pHs, the change of pHs due to the dissolution of a salt. All right. Now, why else could it be important? Why do we want to know about Kas and Kbs, or pKas and pKbs? Well, the value of Ka and Kb tells you the relative strengths of the acid or the base. The larger the value of Ka or Kb, it means that the reaction is proceeding more in the forward direction. That, in turn, is going to be important, because if it proceeds more in the forward direction, it means that it's going to be a stronger acid or a stronger base. Because when we take pKas or pKbs, we're taking the negative logarithm. It's the opposite. The smaller the value of pKa or pKb, the stronger the acid or the base. And those are the values that are given to you on table 15. So be very aware. The smaller the value of the pKa or pKb that you have there, the stronger the acid or the base. As I said at the beginning of when we're talking about why are we interested in calculating the pKb of the conjugate base of a weak acid, or the pKa of the conjugate acid of a weak base, is because when we dissolve salts, all right, the conjugate of base or a conjugate acid of a weak acid or base, they will cause water to hydrolyze and change the pH, and so we need to be able to calculate this. So it is very important that we are able to do this. Okay, so the equations are as we have on the board right now. And so let me give you an example of how we would do this problem. Okay, so if we have a 1 molar solution of sodium ethanoate. Ethanoate is the conjugate base of a weak acid. All right. Now, because it's a salt, it is going to be completely dissociated into the sodium ion and the acetate or ethanoate ions. All right. Now, when we talked about in the SL part, we know that sodium is not a good Lewis acid, and therefore it cannot change the pH of water because it has a very low charge. All right, so it does not affect the pH. But the ethanoate ion is the conjugate base of a weak acid, and therefore it is strong enough to cause the hydrolysis of water, and therefore, because it's a base, it will actually increase the concentration of the hydroxide ion, making the pH greater than 7. All right? So we're going to establish an equilibrium. I'm going to be walking you past this relatively straightforward or relatively quickly. We take the ethanoate, which was produced, all right, and it's the concentration of the ethanoate is equal to the concentration of the salt because it completely dissociated. All right, and it reacts with water to give you ethanoic acid and hydroxide. All right, and we see that initially we have these concentrations. Now, because of the stoichiometry, we're going to consume some of the ethanoate ion to make ethanoic acid, and we're going to make some hydroxide. The water is going to be consumed, but we don't care about the water because the water is a pure substance, and so the concentration will not change. It is included in the Kb equilibrium constant. All right? Now, this allows us to establish equilibrium values of 1 minus x, x, and x for the different species that are going to go into our Kb. Now, we don't have the value of Kb, or even pKb for that matter, for ethanoate. And so we have to calculate it from first principles. We have to remember, oh, that's right, pKa plus pKb equals 14 for a conjugate pair. All right? So if we look in the table, close to the top, we find the pKa for ethanoic acid. It's 4.76. All right? Well, Kb then would be 14 minus 4.76, which means that it's 9.24. The value of Kb is 10 to the negative pKb, in this case 10 to the negative 9.24, which gives us 5.8 times 10 to the negative 10. That's a very small number. Because Kb is a very small number, remember, and we had said over here that the concentration of the ethanoate would become 1 minus x, but because Kb is a very small number, 1 minus x is approximately going to be just 1, then we can rewrite our equation in this form. And when we solve, all right, we're going to take the square root of 5.8 times 10 to the negative 10. We get that it's 2.4 times 10 to the negative fifth is the concentration of the hydroxide ion. We calculate pOH, which ends up being 4.62, and then 14 minus 4.62 gives us the pH, which is our final desired answer. When we dissolve sodium ethanoate and the solution has a concentration of 1 molar, the pH of that solution is going to be basic, and it's going to be 9.38. So we're going to stop here for this video. I'm going to start with salt hydrolysis and a little bit more of that on the next section, and we'll break that section into salt hydrolysis, and then we'll do some buffer work. All right? Thank you. Bye.